Alright, in this video we're going to go through kinetic control and equilibrium. Okay, so this should look somewhat familiar. We've seen these reaction diagrams before. Okay, so I want to look specifically at the first part here. So in the first top part of our diagram here, we know that we've got our activation energy here. We have a certain amount of energy that we have to achieve for the reaction to take place. Okay, so if you think back to physics, when you hear the term kinetic energy, that's particles that are in motion, or objects that are in motion. Okay, so for a reaction to take place, you have to have the correct orientation. You have to have enough speed. So it has to hit with enough speed, and it has to hit in the right orientation for a reaction to take place. Okay, so that's where we fall into the domain of kinetics. Now, thermodynamics, where we're looking at absorbing energy and releasing energy, that's the lower part here. Okay, so we've looked at that before. That's our enthalpy changes. So for a reaction to take place, it's either going to absorb energy or release energy. Okay, so those are the two areas on this reaction curve that we've looked at. We just have kind of like looked at it all at once before. So now we're going to look at kinetics specifically. So if the thermodynamics predict a reaction will take place, but the reaction doesn't occur, we can assume that the reaction is under kinetic control. So we have a very high activation energy, we don't have the right orientation, or we have to have a lot of particles collide at the same time for a reaction to take place. Okay, so a very complicated molecule, for example. Okay, so if thermodynamics predicts that a reaction takes place, we know that one of these factors is going to be responsible. So if thermodynamics says it's going to take place but it doesn't, there's got to be a kinetic issue. Okay. All right. So here's our first example. It says, considering the following exothermic reaction, what's the sign for delta S, what's the sign for delta H, and when will delta G be negative? Oh, and then this reaction does not proceed at room temperature. Can you suggest a change to the conditions that will make the reaction proceed? All right. So first of all, it tells us that it's an exothermic reaction. If it's an exothermic reaction, you're going to have a negative delta H. So that's the easy one. Delta S is our entropy, that's our disorder. So let's take a look at what's happening in our reaction. So we have a gaseous reactant, and then we have two gaseous products. So since we're going from one thing, and now we have smaller particles, we have more of them, there's a lot more going on, this is going to be a positive delta S. Okay, we have more disorder going on because we have more particles. Okay, it's splitting into smaller pieces. When will delta G be negative? Well, let's take a look at the equation. So delta G equals, it's delta S. Let me make sure I have the right equation here. Oh, sorry, delta H minus temperature and delta S. All right, so from our equation, delta H is negative and our delta S is positive. So if I have a negative number and I'm subtracting a positive number, that means that my negative number is just going to get more negative. So when will delta G be negative? Always. There's no way it can be positive in this scenario. All right, D says, this reaction does not proceed at room temperature. Can you suggest a change to these conditions that will make the reaction proceed? Okay. So thermodynamically, it says it's supposed to happen, but it's not happening. So what do we have to do to make the reaction happen? Well, we can increase the temperature, right? We increase the temperature, that's going to cause the particles to move faster and therefore collide with more energy. Let's go back and let's look at the diagram. So we're not having enough, we don't have enough energy to get to the top of the hill. So what if we lower our activation energy using a catalyst? So we keep it at the same temperature, but we throw a catalyst in to lower the activation energy. So add a catalyst. And that's going to decrease the activation energy. So those two things would make the reaction proceed at room temperature. Well, I'm sorry. Raising the temperature would obviously cause the particles to move with more energy. If we add a catalyst, it's going to lower the activation energy. Not necessarily at room temperature. It's saying it doesn't proceed at room temperature. All right, got it. Okay, so K values. K values we've looked at before. If you remember, K values are our equilibrium constant. We use those when we're doing our rate equations. So right, you have like rate equals K, and then you had some concentration X, some concentration Y. So we're talking about this K value right here. So we didn't talk about this specifically in our previous unit, but this is going to be coming up in another unit. We're kind of bouncing around a little bit here. So K values tell us about the position of equilibrium. If K is greater than 1, it shows the products are favored at equilibrium. If K is less than 1, it shows the reactants are favored at equilibrium. Okay, so greater than 1, it's products. Less than 1, it's the reactants. Okay, so we know that if delta G is less than 0, that's favorable. Okay, if delta G is greater than 0, that is unfavorable. If delta G is at 0, we're at equilibrium. Okay, now an easy way to remember this is G and K are going to be opposite. So if delta G is greater than 0, and that's favorable, if K is greater than 1, then it's thermodynamically favorable. So they're opposites here. To be unfavorable, we want K to be less than 1, and we want G to be greater than 0. Okay, so then you're going to be thermodynamically favorable. So the signs are kind of opposite here. Equilibrium, obviously, they're both going to be equal to 0. Okay, so you just need to be kind of familiar with this table here. What is thermodynamically favorable, what is thermodynamically unfavorable, and what that means. All right, so the relationship between K and our delta G is as follows. We have these two possible equations. So if we're solving for K, we're going to use this equation right here. If we're solving for G, we're going to use this equation right here. So there is some criteria for this relationship. So we're going to use the R value of 8.314 joules over moles times Kelvin. Our temperature has to be in Kelvin. Our delta G has to be in units of joules over moles. And then our K value is going to be unitless. That's our equilibrium constant. Okay, so now I know you're probably like panicking a little bit, and that's okay. This looks absolutely crazy, but let's take a look at the resource page that you get to use for the exam. So if you look here, our relationship for delta G is right here. So we have this. We also have, if you forgot, all of the other equations to find delta S, delta H, and delta G. Okay, so we have all these relationships on here. We also have these constants. So our gas constant R is right here. So you don't have to memorize this. This is all on the formula sheet. Okay, so it's important that you know that it's there and where to find it. All right. So let's take a look at an example. Now this is actually going to be a lot easier than you're probably thinking it is right now. So it says calculate the value for G. Okay, and I'm going to throw, since we're solving for G, I'm going to throw down the equation for G. Okay, so we're just going to kind of plug in what we've got. So to plug in, we've got R. We're always going to use 8.314. Our units are going to be joules over moles times Kelvin. We have our temperature in Kelvin, which is 298 Kelvin. Then we're going to take the natural log of our K value, and our K value is given in the question, 1.40 times 10 to the 6th. We're going to take the negative of this whole thing. Now, if you haven't used the natural log button in a while, let me show you where it is on your calculator. Okay, so I'm going to do negative, and I'm going to use two sets of parentheses. So if you notice when I wrote it, I have brackets and then parentheses. So 8.314, and then I've got 298 Kelvin. Okay, and then the natural log button is right here on my calculator, so it's just to the left of the 4 key. So I press natural log. It automatically puts in parentheses for me. So I'm going to do 1.40, and then I'm going to go E to get the exponent, 6, close parentheses, and then one more time. Okay, let me just double check to make sure I got that negative out in front. I did, and enter. Okay, so there's my answer. That is going to be in joules. I need to, let me write that down first. So we end up with an answer of negative 35100 joules per mole. And if I divide that by 1,000, I'm going to get kilojoules, so that'll be 35.1 kilojoules per mole. All right, that's it. So basically just plugging in another equation, okay? And you need to be able to interpret the results. So again, please look over this table so that you know what is favored and what's not favored, what's favorable and what's unfavorable, talking about thermodynamics and our equilibrium constant.